Hello, I have a second video for chapter 17. This will cover 17.4 through 17.6. In the previous video, we talked about how um, things that are spontaneous or thermodynamically favorable are ones that increase the entropy of the universe. Now that's a bit awkward to have to deal with the universe when every time we want to know something about a particular reaction. So Josiah Willard Gibbs, famous for the Gibbs free energy state function, he derived this function in order to only focus on the system and to determine just based on the properties of the system whether or not a process change in that system would be favorable or not. And so he is famous for this Gibbs free energy function. So the Gibbs free energy function, capital G, is equal to the enthalpy minus the absolute temperature times the entropy. So for any particular system, the Gibbs free energy is its enthalpy minus its temperature times its entropy. Now, this may seem a bit random, but it was all very purposeful. One of the ways that we tend to deal with the Gibbs free energy function is to talk about changes in Gibbs free energy. You know, we like our deltas, delta H and delta S and delta T. So delta G, if we only consider things that happen at constant temperature and pressure, which would be the conditions kind of on the lab top table, right? Constant temperature, room temperature, constant pressure, 1 atmosphere. So if we consider those type of changes, the ones that occur in open systems at constant temperature and pressure, these changes can be analyzed by their delta G. And the change in Gibbs free energy would be the change in the enthalpy minus the temperature times the change in the entropy. So it's pretty obvious by how we've set this up that we need to keep temperature constant because there is no delta T in this equation, just T. So temperature would need to be constant. However, the enthalpy of the system will change. There will be heat given off or heat absorbed. It will be endothermic or exothermic. And the entropy will change, either positive or negative, depending on whether the system becomes more disordered or less disordered. But we're using constant temperature. You might be wondering, why are we using constant pressure? Well, don't forget that in Chapter 6 we learned that delta H is the heat flow at constant pressure. The definition of delta H, or change in enthalpy, was the heat flow at constant pressure. So we have these constraints on us. We want to do this at constant temperature and constant pressure. It is possible to do these things at other conditions and allow pressure and temperature to change, but it's more complicated. So we're starting out simple here with this relationship delta G equals delta H minus T delta S. Now, to get a little insight into why he developed this particular relationship, why he chose H minus TS to be his capital G, let's take this equation, delta G equals delta H minus T delta S, and let's divide both sides by negative T. Now go with me here on this because we're doing this for a reason. So the left side would look like negative delta G over T, and that would equal negative delta H over T. And because we divided by negative 1 over T, the T's cancel in the last term, and you would just have positive delta S. And all of these would be for the system. Now, if you recall, negative delta H over T, that was the equation for the change in entropy of the surroundings. So what we have done here by dividing both sides by negative 1 over T, or dividing both sides by negative T, I guess, or multiplying by negative 1 over T, is we have created the right side of the equation now is equal to delta S of the surroundings, negative delta H over T, plus delta S of the system, delta S. And so what we've done is we've converted this equation so the right side of the equation equals delta S of the universe. So what we're finding here is that this negative delta G over T, if you take the Gibbs free energy change and divide it by negative T, you actually get the delta S of the universe. And so there is a relationship here between delta S of the universe and delta G. And since delta S of the universe can be used to determine if something is thermodynamically favored, then delta G can also be used to determine that. Now the signs are opposite, so if for thermodynamic favorability we want the delta S of the universe to be positive, then for Gibbs free energy we want the change in Gibbs free energy to be negative. So keep that in mind. If you want something to be thermodynamically favored, it needs to have a negative change in Gibbs free energy. But now we have a property of the system. We don't have to use the surroundings as part of our math in order to determine if a process will be thermodynamically favored. So we've got our delta G and the delta S of the universe, and they can both be used to determine thermodynamic favorability. We either want a negative delta G or a positive delta S of the universe. Now, to actually find delta G, we're going to need to have some way of finding the delta S of the system. Now, we already know we can find the delta S of the surroundings. It's just negative delta H over T. But how do we find the delta S of the system? We're going to need to find the delta S of the system from the delta S of the surroundings. But the only way to do that is to find a particular set of conditions where we can relate the delta S of the system to the delta S of the surroundings. So let me use this melting of ice example again. I believe we've used it previously, but let's go back to this melting of ice example. H2O solid yields H2O liquid. So we know for this process of melting of ice, that below 0 Celsius, the process is not spontaneous. It's not thermodynamically favorable to melt ice below 0 Celsius. So in that case, we would say delta S of the universe is negative. Now, got all kinds of misspellings here. Above 0 Celsius, the process is spontaneous, so delta S of the universe is positive. Well, if below it's negative and above it's positive, that must mean that at 0 Celsius, delta S of the universe is 0. Well, if delta S of the universe is 0, then, and it equals delta S of the system plus delta S of the surroundings, that must mean at 0 Celsius, this process, that the delta S of the system equals the negative delta S of the surroundings. So as long as you go to the conditions where a process is at equilibrium, it's not favored in forward or direct or reverse direction, it's kind of on its tipping point between being a positive or a negative delta S universe or being favored or not favored. If you can find that point, then you can actually get the delta S of the system for those conditions from the negative of the delta S of the surroundings, because they have to add up to 0. So, as you can see, delta S system can be found, and in fact is equal to delta H over T for that particular change. So whatever heat flow occurs for the system during a particular change in the system, by dividing it by T, you're getting delta S of the system. Now, this is only true at exactly the point where it tips. But it does give us a way to begin kind of getting some values for delta S of the system. Now, in reality, delta S of the system is not that dependent on temperature. Delta S of the surroundings is the part that's dependent on temperature. Remember, delta S of the system is more about the positional entropy. And so, even if you're not exactly at the tipping point, this delta H over T approach is actually still pretty good and gives you a pretty good estimate of delta S of the system. And there are some more complicated ways to make the corrections that are needed for changing or finding the change in entropy of the system if you're not exactly at that tipping point between favorable and not favorable. But kind of interesting that you can get your delta S of the system by just knowing the heat flow and the temperature of this tipping point. So to illustrate this, let's take a look at why the process is favorable above 0 Celsius and not favorable below 0 Celsius. So if we take the temperature of negative 10 Celsius, which is below freezing, or 263 Kelvin, the delta H at negative 10 for melting is positive because you're putting in heat, 6.03 times 10 to the third joules per mole. And notice it's the same for negative 10, 0, and 10. Delta H is also not that temperature dependent. As long as you're staying close to the same value of temperature, your delta H will be pretty similar for any particular reaction. Delta S of the system is also fairly constant. Notice it's 22.1 at negative 10, and it's still 22.1 at 0, and it's still 22.1 at 10. So we're seeing that as long as you're staying close to that the same temperature, you can expect the delta H and delta S for a particular chemical or physical change to be a fairly constant value. However, delta S of the surroundings is highly temperature dependent. Remember, it's negative delta H over T, so T is in its formula. And it's going to be negative 22.9 at negative 10, negative 22.1 at a higher temperature, and negative 21.3 at the even higher temperature of 283 Kelvin. So if you wanted to do the math on that, you can see you could take your delta H, 6.03 times 10 to the third, and divide it by 263, and you will get your negative 22.9 back. Excuse me. So then if we take and add the delta S to the delta S of the surroundings, so this would be the delta S of the system, 22.1, to the delta S of the surroundings, negative 22.9, we find that the delta S of the universe is negative 0.8. So we get a negative delta S in the universe. So that means that it is not thermodynamically favorable to melt ice at negative 10 degrees. Now, just for to take a look at this Gibbs free energy function, T delta S would be 263 times 22.1, which comes out to 5.81 times 10 to the third. And then delta H minus T delta S would be 6.03 times 10 to the third minus 5.81 times 10 to the third. And so that would be 2.2 times 10 to the second joules per mole. So notice for trying to melt ice at negative 10 Celsius, delta G is positive. Now you do that same math on 0 Celsius and 10 Celsius, and you find it's 0 at the tipping point of 0 Celsius, but then above freezing, water spontaneously melts. Let's take a look at some various combinations of delta H and delta S and think about how they would play on spontaneity, on thermodynamic favorability. If your delta S is positive, that means that if you take delta H minus T delta S, that the minus T delta S is trying to make delta G negative. And that's something that would make things more spontaneous. What else will happen, will help delta G to be negative, is if you have a delta H that is negative. So looking at the equation, delta G equals delta H minus T delta S, a negative delta H and a positive delta S are going to combine to always give you a negative delta G, because temperature is always a positive because it's in kelvins. So that we would say if your delta S is positive and your delta H is negative, you're going to be spontaneous at all temperatures. There might be some temperatures that you're more spontaneous, but you're going to be spontaneous at all temperatures. However, if your delta S is positive, which is what we want, negative T delta S will give us a negative delta G if delta S is positive, but your delta H is positive, now the two are going to go to battle. The delta H is going to be positive, trying to make delta G positive, but the delta S is positive, trying to make delta G negative. And so it depends on which one wins. Well, at high temperatures, delta S wins. So at high temperatures, you're going to be subtracting a bigger T delta S from your delta H, and your delta G is probably going to be a negative value if you get the temperature high enough. So for endothermic processes, to get them to be favorable, you raise the temperature, because at the higher temperature, the positive delta S will help you get the reaction to be favorable. So think about that. Endothermic, we raise the temperature of things, right? We heat endothermic reactions to get them to happen. It's because of what we just described there. Now, if your delta S is negative, but your delta H is negative, now you've got a favorable delta H, but an unfavorable delta S. So in that case, you want your temperature to be low so that your T delta S term is not going to be outweighing your delta H term. You want your negative delta H to win so your delta G can be negative so you can be spontaneous. So these kinds of analysis of signs of delta H and delta S and delta G are all very important on the AP test. So being able to analyze this equation, delta G, delta H minus T delta S, just in terms of what sign of delta G are we looking for, what does that mean about the sign of delta H, what does that mean about the sign of delta S, and what's that mean about the size of the temperature, and how are they going to play together in such a way as to give you either a negative delta G or a positive delta G, or a spontaneous thermodynamically favorable process, or a non-spontaneous, not thermodynamically favorable process. So let's practice finding out whether or not a process is spontaneous using delta G. So we know for the boiling of bromine, the bromine is a liquid at room temperature and boils at a particular temperature. So Br2 liquid yields Br2 gas. The delta H for this process is positive 31 kilojoules per mole. We'd expect it to be positive because we're breaking some bonds, or we're going to have to break some London dispersion forces to turn liquid bromine into gaseous bromine. And they're fairly strong because Br2 has quite a few electrons. So remember, London dispersion forces are stronger when you have a bigger molecule with more electrons. The delta S for this process, because we're going from a liquid to a gas, is also positive, so it's 93 joules per k mole. So looking back, we have a positive delta H and a positive delta S, so we expect this to be spontaneous at high temperatures, but not spontaneous at low temperatures. So that's what we find. Boiling occurs at high temperatures, but not at low temperatures. Now, below the boiling point, the delta G is going to be positive. Above the boiling point, the delta G is going to be negative. At the boiling point, the delta G will be 0. Let's find that boiling point, and then below that, we'll know the boiling point. Below the boiling point, that delta G will be positive, and above that, delta G will be negative. So let's go ahead at the boiling point and set delta G equal to 0. So now 0 equals delta H minus T delta S. So for that to be true, T delta S equals delta H, or T equals delta H over delta S. Just doing a little algebra manipulation there. So we're solving for the temperature where delta G is 0, and it's the temperature which equals the ratio of the delta H of the process to the delta S of the process. Now, because delta S is in joules and delta H is in kilojoules, I'm going to need to convert delta H to joules. So 31 kilojoules is 31,000 joules per mole. Delta S is 93 joules per Kelvin per mole, and the ratio of the two numbers is 333. The joules per mole cancel out, and we have Kelvin as our unit. 333 Kelvin, which would be about 60 degrees Celsius. So below 333, delta G is positive, and the process is not spontaneous. At 333, actually I should say above, let me check that and fix that. We should say above 333 Celsius, or 333 Kelvin rather, the process is spontaneous because you'll have a negative delta G above 333 Kelvin, And that means the boiling point of liquid bromine, where delta G is 0, because it's in between being not spontaneous and being spontaneous, is 333 Kelvin. So interesting that you can find something's boiling point from data about its enthalpy change and its entropy change for a particular boiling process. Now let's think about entropy in dissolving. We know that like dissolves like. So that is sort of the natural tendency of things. It's thermodynamically favorable for ionic salt to dissolve in water. So let's look at that process by analyzing the delta H and the delta S. Just a minute, and I am going to have to pause here. Hello. Yes. It's okay upstairs. It's fine with me. Yeah, sure. No problem. Bye. Okay, sorry about that. Feel free to fast forward through that little pause there. Just had to answer the phone real quick. Okay, so we're talking about dissolving salt, and we know that the delta H for dissolving salt is a positive number because we're breaking bonds, and we can also tell from the solubility graph that salt dissolves better at high temperatures, so Le Chatelier's principle, put in heat, shifts to right, all this kind of analysis. We know the delta H is positive. Well, that's not the kind of delta H we really like. However, I think we're going to still be able to dissolve salt because the delta S is positive. And that's because going from an ordered ionic crystal to a disordered solution is actually going to give you a positive delta S. So you can see why salt is able to dissolve and why it's able to form a solution is that the T delta S term is going to outweigh the delta H term, and in fact will outweigh it even more at a higher temperature, which is why salt dissolves better at higher temperatures. Up to a point. We know salt has a solubility limit, so there is a concentration at which the T delta S no longer outweighs the delta H and you reach an equilibrium. For an equilibrium, delta G is 0. So there is a tipping point where the delta H becomes too positive and the delta S is not positive enough to outweigh the delta H, and your delta G can no longer support dissolving. Now we have to be careful here not to generalize because not every ionic solid has a positive delta S of solution. Now this may be surprising to some people. You may think, well, a crystal is ordered, dissolved is not ordered. So what's going on? Why wouldn't every ionic solid dissolving in water always give you a positive delta S? Well, that's a general rule of thumb that they will. However, when you have very strong Coulombic forces between the ion and the water, the ion's effect on water will be to create quite a bit of order in the water. And so we're thinking mainly of the ions, but think about what's happening to the water. The water is surrounding those ions and creating those hydration spheres, and those hydration spheres are in fact lowering the entropy of the water. So it is possible under certain conditions, either very high concentrations or for some ionic solids, even fairly low concentrations, for the change in entropy of the water to outweigh the change in entropy of the ionic solid. Now we see here that for KCl, they're only +1, -1, and it has a fairly large ions, so you're going to have a good positive delta S of the solution. However, LiF with the smaller ions, a little bit stronger Coulombic forces in those ion dipole forces. CAS with the +2, -2, a little bit stronger Coulombic forces. And when Coulombic forces become greater, your delta S solution may actually flip to become a negative value, which means it is not going to support dissolving. However, at the same time, you're also getting your delta H to be um, more, let's see, because you're breaking stronger bonds, it's becoming more positive. And so these, typically when we talk about ionic solids not being soluble or being soluble at very low levels, it's because they have strong Coulombic forces both in the crystal, which means you have to break strong Coulombic forces, but also in the water, which means it lowers the entropy of the water, both of which are sort of counterproductive for getting dissolving to occur. Now, if we flip to gases, I don't think the book really addressed gases, but gases dissolving in water, they're actually going to have negative enthalpies, because negative heats of solution, because they're going from gases which do not have attractive forces to being in the liquid state dissolved in the water, which will give it attractive forces. So typically gases dissolving in water have negative delta H's, but at the same time, they're going to have negative entropy changes because they're going from free gases spread out to being now crowded in with water molecules, and that's going to tend to lower their entropy. So in that case, where we could analyze the signs, negative delta H, well, that's good. Negative delta S, that's bad. So we would expect at higher temperatures that solubility would actually go down, and that is what we see, that gases tend to be driven out of liquids that they're dissolved in when you raise their temperature. And so you see how powerful this understanding the interplay of delta H and delta S can be in analyzing various scenarios. You really want to practice that and think it through. And if you ever come up with one that doesn't fit your model, go ahead and ask it in class, and we'll see if we can analyze why the combination of delta H and delta S doesn't give you the effect that you expect. But what you're seeing here is the sign of delta H and delta S can often play with temperature in such a way as to make things favorable under one temperature condition and not favorable under another. Now, we've mainly been focused on physical changes like dissolving and boiling and melting, but the same principles for entropy changes and for enthalpy changes apply, and thermodynamic favorability apply to chemical reactions. It is possible to use Gibbs free energy to find out if a chemical reaction should be favorable, and whether it should be favorable at low temperatures or high temperatures or both. So to look at an example and just talk about it qualitatively first, let's look at the ammonia synthesis, the famous Haber process, N2 plus 3H2 yields 2NH3. Starting out with entropy here, we would expect, because we're going from 4 gaseous molecules to 2, that our delta S will be negative. And when you calculate the values, it is indeed. The delta S is negative because you're going from 4 gaseous molecules to 2. For any system, that kind of gives us a rule of thumb. For any system, your entropy changes are mainly about the positional entropy. So it's mainly about how many molecules you have and what is their state, gaseous, liquid, solid, and what is how many different ways can you arrange them. So there are more ways to arrange 4 molecules than there are to arrange 2 molecules. So delta S is negative. When a reaction involves gaseous molecules, positional entropy is going to dominate, and you're going to want to look at the relative number of molecules of gas. If there's a gas in your equation, count the moles of gas on the left, count the moles of the gas on the right, and you can draw your conclusion about delta S. So for example, taking a look at an example 17.6 out of the book, calcium carbonate solid yields calcium oxide solid plus CO2 gas. We're going from a solid to another solid plus a gas. So we expect the gas with its very high entropy to result in this being a positive sign for the delta S. 2SO2 plus O2 yields 2SO3. The left side has 3 moles of gas, but the right side has 2, so we expect a negative sign for our delta S. Now, in most of our thermodynamics, we're mainly interested in changes. Delta G, delta H. And that's actually because absolute values cannot be determined. If you remember in the back of the book, it didn't give values for H, it gave values for delta H of formation. We had to sort of set an arbitrary zero and then talk about being above and below that arbitrary zero. We set for delta H, we set the zero to be elements at 25 Celsius and 1 atmosphere. That's 0, 0. Now let's talk about compounds being either above or below that zero line. This is very similar to what they do with Celsius scale. The Celsius scale, they set the freezing point of water to be 0, and you're either above or below that. Now, absolute values would be something like absolute temperature, kelvins. 0 really means 0. 0 is not an arbitrary setting where you can go above or below. So sometimes we can get away with just knowing changes in certain functions, but it's actually possible for entropy to know it absolutely as we do with temperature in the Kelvin scale. We do have a definition for 0 entropy, just like 0 Kelvin is when all molecules stop moving. 0 entropy, and this is actually the third law of thermodynamics, is when you have a perfect crystal at 0 Kelvin. A perfect crystal at 0 Kelvin has no disorder and has no entropy, so its entropy is 0. As a result, in Appendix 4 in the back of the textbook, you may notice that the entropy values do not have a delta in front of them. The enthalpies and the delta G's are in the back of the book. They have a delta in front of them, but the entropies are actually absolute entropies. They're just S's. Now remember that superscript 0 sign there means that you're doing things under standard conditions. So, thinking back to our algebra from using the back of the textbook, it was always delta H formation of the products minus the reactants. In the same way, we can use the back of the book to find the entropy change for a particular chemical process or physical process by simply taking the sum of the products minus the reactants again. Just in this case, it's not deltas. Do be conscious of the fact that S's are in joules, H's and G's are going to be found in kilojoules. So to practice this equation, remember this is really sort of a version of Hess's law. Delta S for the reaction 2NiS plus 3O2 yields 2SO2 plus 2NiO. We have this list. These numbers could be looked up in the back of the book, but we put them right here in a little table for the SO2, NiO, NiS, and O2 values. Now, delta S is going to be products minus reactants. So we have 2 moles of SO2. So we take 2 times 248, 2 moles of NiO plus 2 times 38. Now we've summed the products. Minus, put it in brackets, sum the reactants. 2 times 53 for NiS and 3 times O2, 205. And you end up with a negative 149 joules per Kelvin. Now, are we surprised that it's negative? No, we have 3 moles of O2 on the left and 2 moles of SO2 on the right, so we're actually losing a mole of gas, so we would expect a negative delta S. Now, I do want to point out here, you may be in the habit from chapter 6 of treating elements always as having a value of 0. Do not do that with entropy. That's a major stumbling block for students. They get used to calling elements 0, but a mole of oxygen gas at room temperature and 1 atmosphere definitely does not have 0 entropy. It has a value. In fact, it's the biggest of the 4 things in this problem. So do not call elements 0. 0 is a perfect crystal at 0 Kelvin. Now, they do another example very similar in the book. I didn't go ahead and do it again, but it's Al2O3 plus 3 hydrogen yields 2Al plus 3 waters. And if you go through the math, you'll see that the delta S for that is positive 179 joules per Kelvin. Or you might say joules per Kelvin per mole of reaction. But typically we consider the moles to have canceled out in the formula for delta S. Now, you might look at this and go, wait a minute, why is it such a large change in delta S? You've got 3 moles of gas on the left and 3 moles of water vapor on the right and 3 moles of gas on each side, so why is there such a large change in delta S? And it's actually due to the difference in entropy of the hydrogen molecule compared to the water molecule when they're both in the gas phase. Hydrogen is simply 2 atoms connected by a single bond. That single bond can stretch a little bit and the hydrogen can move left and right and up and down and in and out, but not a lot of ways that hydrogen can use energy. However, water's got many different vibrational modes and rotational modes and stretching modes and changing of angles and changing of bond lengths. And as a result, water is much more complex. It has a lot more positional entropy. There are many more ways to position the 3 atoms in a water molecule besides the fact that there are many ways to position the water molecule in the gas phase. So, as a result, the general rule of thumb would be the more complex your molecule is, the higher its entropy. So in this case, the 3 hydrogen gas makes 3 water vapors. The water is going to have more entropy than the hydrogen, even though there's equal moles of gas. Okay, I'm going to stop there and try to upload this video for you guys.